Imagine a space stretching infinitely in all directions, the absolute emptiness and sterility of a room where there is not even the smallest speck of dust and where no light penetrates at all. Now place a flashlight in this void. Wonderful, but there is one inaccuracy in this description. In fact, the picture should look like this. If we were in the aforementioned room and looked at even a lit flashlight, we would not be able to see either the flashlight itself or the beam of light it emits. Paradoxically, light itself is invisible, and this invisibility is one of its most fundamental and understandable properties. We only see light when it directly enters our eyes. We are unable to perceive light that simply passes by us without reflecting off anything. If there were a second light source in the room, we would be able to see the flashlight itself, but again, not the beam of light coming from it. Light rays, even from the most intense source available to us, pass through each other as if there were no obstacles in their path. Remember this important observation, because in the next few minutes it will change the way you think about reality. And if you want more explorations like this, make sure to like the video, leave a comment, and subscribe so you don't miss what comes next. Now imagine that the flashlight is pointed directly at your eyes and you begin to gradually move away from it, moving backward. The flashlight's reflector will appear smaller and smaller to you, and then it will turn into a barely discernible dot. As you move further away, this dot will become dimmer and dimmer. When the distance between your eyes and the flashlight reaches 10,000 kilometers, the dim spot will disappear from view altogether. But this is true only if we are talking about human vision. A frog's eye is several times more sensitive than the human eye. This difference is enough to make the experiment yield a significantly different result if the observer is a frog. If the frog moves away from the electric flashlight, the moment when it completely loses sight of it will never come. Instead, the frog will begin to observe an interesting picture. It will see that the flashlight has begun to flash at irregular intervals. These intervals between flashes will become longer and longer as the frog moves away. At a distance of 100 million kilometers, the frog will perceive, on average, only one flash of light per day. But each such flash will have the same brightness as any other flash observed throughout this infinite distance. This flickering proves the existence of a limit to the uniform stretching of light. Each flash that the frog sees is caused by a separate photon hitting the retina of its eye. As they move away from the flashlight, the photons themselves do not become weaker. The light beam weakens because the empty free space between the individual photons increases. When the frog does not see the light, it is not because the light reaching its eyes is too weak, but because no photons are reaching its eyes at that moment. This property of light to manifest itself only in the form of separate, indivisible pieces of discrete sizes is called quantization. A separate piece of light, a photon, is called a quantum. Quantum theory got its name precisely because of this key property, which it attributes to all measurable physical quantities. According to modern physics, there are no measurable quantities that are continuous in nature. Everything that surrounds us and seems continuous is actually not so. This video is based on the book The Fabric of Reality by British theoretical physicist David Deutsch. It is his magnum opus, his most important work. In the book, Deutsch presents his, at times, ultimate view of what the universe is. It must be said that he presents it in a rather confusing way, probably because he is primarily a scientist, not a writer. Therefore, I have quoted some passages from the book directly, rewritten and edited others, provided different examples in some places, and added a lot from alternative sources, all in order to achieve a more complete picture and make Deutsch's ideas more accessible. His ideas are quite interesting, although I would not say that I completely agree with everything written here. It is unclear whether this is because the author does not always express his thoughts clearly and concisely, or simply because I am not smart enough to fully understand him. David Deutsch, is such a rebel of science. With this book, he has certainly caused a lot of controversy in scientific circles. But this video will most likely be about something else entirely. It will be about why we almost certainly live in a multiverse. The terms multiverse, parallel reality, and alternate worlds have become commonplace in our everyday vocabulary. Almost everyone uses these phrases in everyday life. For example, when talking about unlikely events. In one of the parallel universes, I'm a billionaire. But let's be honest, no one takes the idea of a multiverse seriously. Most people don't even know what this idea means in the context of physics. In fact, it means many things. a multitude of inhabited worlds described by completely different physical concepts, and many of these concepts have a right to exist. We will talk about the many worlds interpretation of quantum mechanics, which, being both direct and almost the simplest consequence, presents us with a whole new view of the world. Wait a second, so new that when scientists began to gradually discover the laws of quantum mechanics, they naturally tried to explain what they were seeing. They tried this and that, but in the end, they gave up. Today, among quantum theory specialists, it is considered rather bad form to talk about anything other than equations. Any attempt to explain what these equations mean is immediately dismissed as empty chatter. David Deutsch, in turn, despises such an imminent approach to physical theory. From his point of view, and I absolutely agree with him on this, the desire not only to predict and use, but also to understand is absolutely normal. You know what's strange? Quantum mechanics is the most proven and successful theory in the history of science. The main proof of this fact is that you are watching this video at all, because it is quantum mechanics that became the theoretical basis of semiconductor electronics. And yet, I repeat, we have no understanding of what it is. If, for example, Einstein's general theory of relativity tells us about the curvature of the space-time continuum, then no one knows what quantum mechanics is talking about. All we have are interpretations, and all we can do is argue about which one is better. Okay, so what is the mystery of what happens at the quantum level? I'm sure you've heard about the double-slit experiment many times. If not, I'll briefly describe it now. Feynman liked to say that all of quantum mechanics can be derived from careful consideration of the consequences of this single experiment. So let's take a piece of foil and make two small slits in it, 1.5 millimeters apart. Let's place a screen behind the foil. We take a regular laser and shine it on the slits in the foil. If light traveled in a straight line, we would see two bright bands with sharp boundaries located 1.5 millimeters apart. But in reality, we get a multitude of bright and dark bands without sharp boundaries. Quite unusual. Okay, what kind of shadow will we get if we cut two more slits between the two slits in the remaining space, so that we have four slits located at a distance of 1/10 of a millimeter from each other? One might expect that the picture would look almost the same, but in reality, something completely different happens. We see that the shadow from the four slits is by no means a combination of two slightly shifted shadows from the two slits, but has a completely different structure. In this picture, there are areas such as point X. These areas were illuminated when there were two slits in the partition, but suddenly ceased to be illuminated when two more slits were cut in the partition to let light through. Thus, the appearance of two additional light sources darkens point X, and their removal illuminates it again. What nonsense! Nevertheless, the main idea cannot be avoided. Something passes through the second pair of slits that prevents light from the first pair of slits from reaching zone X. But what is it? Whatever is causing the interference is obviously located in the light beam itself. And whatever it is, it behaves exactly like light itself. It is always present in the beam of light, but absent outside it. It is reflected, transmitted, or blocked by what reflects, transmits, or blocks light. The only answer that comes to mind is that it is light itself, that is, photons. Photons from one slit interfere with photons from other slits. But how can they interfere if photons do not interact with each other? Remember I mentioned this at the beginning of the video? Okay, fine. What if they do interact? If we conduct the same experiment but shoot from the laser, just in case, only one photon at a time, we will get exactly the same result. Even when conducting an experiment with single photons, we will not see a single case of them hitting point X if all four slits are open. But as soon as the two slits are closed, the flashes at point X immediately resume. Perhaps after this we can assume that the photon does indeed split into fragments which change their trajectory after passing through the slits and then rejoin. But this is not the case. By installing a detector at each slit, we will never record the simultaneous activation of even two detectors. So what happens when we fire one photon at a time in our experiment? Something penetrates the other slits and interferes with the original photon. This something is intangible, invisible, and we cannot register it with instruments. Let's take a critical look at this question then.
We have found that when a single photon passes through this apparatus, it passes through one slit and is then affected by some force that causes it to deviate from its original trajectory. This effect depends on which other slits remain open. That is, the objects that affect the photon themselves pass through other slits and behave similarly to photons, but they are invisible. We can assume that these are some kind of shadow photons that can only be detected indirectly through their influence on real photons. So each real photon is accompanied by an escort of shadow photons. When a real photon passes through one of the 4 slits, some shadow photons pass through the other slits. The number of these shadow photons is obviously far exceeds the number of real ones. Deutsch and his colleagues concluded that there is no upper limit to the number of shadow photons, but the minimum possible number is 1 trillion shadow photons for every real one.
Now, follow this line of reasoning carefully. What must happen at the microscopic level when shadow photons encounter an opaque barrier? They must stop. We know this because interference ceases when an opaque barrier appears in the path of the shadow photons. But what exactly stops them? They certainly cannot be absorbed by the real atoms of the barrier because, given the presumed enormous number of shadow photons, the barrier would simply evaporate before our very eyes. In short, we would easily detect this in many different ways. Shadow photons do not interact with real atoms, and yet the wall affects both real and shadow photons in the same way. It stops them. But shadow and real photons, in turn, affect the wall differently. In fact, as far as we know, shadow photons have no effect on it at all. And yet, they are stopped. And therefore, you know what? Therefore, along with the existence of the real partition, there is also its shadow twin. This is simply an inevitable conclusion. Without much effort, we understand that this shadow partition consists of shadow atoms, in which, as we already know, there must be twins of the real atoms of the partition. Each real atom has many such shadow doubles. In fact, the total density of shadow atoms, even in a thin fog, is more than enough to stop a tank, let alone a single photon. If these atoms could have any effect on it, here you may stop me and say, well, these are far-fetched conclusions. And the same goes for the microcosm. How can we talk about entire parallel universes based solely on interference of photons? Light quanta, big deal. They don't even have mass. But we already have an interference pattern on fullerene molecules. Fullerene is a form of pure carbon. Do you understand this? It's practically a classic object. In other words, particles are grouped into parallel universes. They are parallel in the sense that within each such universe, particles interact with each other in exactly the same way as in our real universe. But the influence that each universe has on the others is very weak and manifests itself through the phenomenon of interference. Thus, we have constructed a chain of reasoning that begins with strange shadow patterns and ends with the existence of parallel universes. At each stage of this reasoning, we find that the behavior of the objects we observe can only be explained by the presence of invisible objects and their specific properties. The main idea is that interference of a single particle irrefutably excludes the possibility of the existence of only the real universe that surrounds us. Nevertheless, the theory of the existence of a multiverse has not been particularly popular among physicists for a long time. Why? Because its conclusions are obviously too grandiose to be accepted unconditionally. Some practicing physicists ask, why can't we just say that photons behave as if they collide with invisible objects? Why go further and accept the theory of the real existence of these invisible objects? A real photon is tangible, while a shadow photon is simply a way of describing the possible but unrealized behavior of a real photon. Quantum theory, in their opinion, consists of the interaction of the real with the possible. Why can't we leave it at that? Because, as Deutsch says, the impossible cannot interact with the real. Non-existent objects cannot change the trajectory of existing ones.
If a photon deviates from its path, something real must affect it. It cannot be that a real event, the appearance and detection of a real photon, is caused by an imaginary event, something that another photon could do later. As I have already said, interference is not unique to photons. Quantum theory predicts and experiments confirm that interference occurs with any particle. Thus, every real electron must be accompanied by a mass of shadow electrons, every real neutron by a mass of shadow neutrons, and so on. Consequently, reality is much greater than it seems, and most of it is invisible. We could call the totality of all shadow particles a parallel universe, because shadow particles are affected by real particles only through the phenomenon of interference. But we can go even further. After all, shadow particles are separated from each other in exactly the same way as the universe of real particles is separated from them. In other words, they form not one homogeneous parallel universe, much larger than the real one, but a huge number of parallel universes. Each of them is similar in composition to the real one and obeys the same laws of physics, but differs from the others in the arrangement of particles. Let's return to the experiment with two slits. What will happen if we place detectors near each slit and try to catch the split photon as it passes through both slits? In this case, the quantum will always be recorded as coming out of only one slit, but never from both at the same time. This is logical, considering that quanta are by definition indivisible. But the interference pattern on the screen suddenly disappears, replaced by a normal distribution in two bands. You might say, well, yes, that's not surprising. After all, at the subatomic level, it is impossible to measure anything without interaction, and attempts to find out which slit the photon flew through simply cause the detector to influence it and change its behavior. Okay, so be it. However, if only one detector is installed at only one slit, the quantum, even without being caught and passing through the other slit, will still not show interference. That is, the quantum, just think about this, somehow knows that it's being measured at the other slit and refuses to interfere. In other words, the mere possibility of obtaining information about which slit the photon flew through deprives us of the opportunity to see interference. It's just mystical. Indeed, this has given rise to almost an entirely new religious movement, the materiality of thoughts. The observer influences the universe by the mere fact of his observation. What do you think contributed to all these prejudices? The classical interpretation of the founding fathers of quantum mechanics. The classical interpretation, or as it's also called, the Copenhagen interpretation, is the most common point of view among those scientists who have decided to accept any explanations at all. Its adherents divide the world into quantum observable objects and classical measuring instruments, which in itself is quite strange. Thus, our photon, a quantum object, behaves like a probability wave before measurement, flying through the slits. That is, it is in a superposition of quantum states. But as soon as this probability wave interacts with a classical system, a screen or a detector, it instantly collapses, turning into a particle in a specific location. That is, until the photon is observed, it is a wave, but at the moment of measurement, it becomes a particle. In the Copenhagen interpretation, this is called wave function collapse. Albert Einstein once exclaimed, "I would like to believe that the moon continues to remain in its place even when no one is looking at it." You cannot imagine how many times and in how many different variations the double-slit experiment has been conducted in an attempt to restore common sense to everything that is happening. All of these attempts have been in vain. This all sounds absurd, to say the least. Absurd within the Copenhagen interpretation, and despite the fact that this interpretation has gathered the majority of followers, David Deutsch argues that in reality, no scientist has believed in it for a long time. In 1957, American physicist Hugh Everett was the first to clearly realize that quantum theory describes a multiverse. At that time, almost no one listened to him, but now many experts agree that it is the many worlds interpretation that resolves almost all questions related to the oddities of the subatomic world. What does Everett's many worlds interpretation actually say? It asserts that when observed, interference actually does not disappear anywhere.
Moreover, the statement, observation destroys interference, is highly misleading for 3 reasons. First, it implies the existence of some kind of psychogenetic influence of the conscious observer on fundamental physical phenomena, although unfortunately no such influence exists. Second, interference is not destroyed, but simply becomes much more difficult to observe, since this requires controlling the precise behavior of a much larger number of particles. Third, not only observation, but also any impact of a photon on its environment, which depends on the trajectory it chooses, leads to the same effect.
And most importantly, am I really a billionaire in one of the parallel universes? First, what is meant by I? It is no longer me. One can draw a rather crude but apt analogy with identical twins. Genetically, they are absolutely identical. We were once a single zygote, but can we now claim that your twin is you? Especially since the differences between you will only increase over time. Second, no one can say for sure how many universes there are. If there are a finite number of universes rather than an infinite number, then there are events so improbable that they do not occur in the multiverse. If there are an infinite number of universes, then everything that can happen happens in the multiverse. Everything that does not contradict the laws of physics, including the universe where the sun has just exploded because all its atoms accidentally rushed to its center. Of course, this event is on an extremely thin branch of probability in the multiverse, but such a branch exists there. Strictly speaking, in this case, there are an infinite number of universes in which the sun has exploded. But this infinity is incomparably thinner than the infinity of universes in which the sun feels normal. Yes, despite the fact that there are an infinite number of both types of universes, their densities are different. If this is unclear, here is a simple example. The infinity of natural numbers isn't greater than the infinity of even numbers. Surprisingly, they are equivalent. However, infinities are indeed different from each other. I'll talk about it in the next video somehow. Like and comment so I know what topic you want to see a video about. The multiverse interpretation, unlike the Copenhagen interpretation, asserts that the entire world is quantum. This is much more consistent than the Copenhagen quantum classical world. In the many worlds interpretation, there is no mystical observer who causes the collapse of the wave function. Instead, there is a process of constant splitting called decoherence. In the 2-slit experiment, photons pass through the slits in all possible ways at the same time, and by measuring a photon, we become entangled with it and split ourselves into all possible versions of ourselves that have measured the photon in all possible states, thereby spreading across the branches of probability in the multiverse. You may ask, what is measurement? How does the universe understand that the photon will be measured and the pair splits? This is where the law of entropy comes into play. Entropy is a measure of the irreversible dissipation of information. Measurement is any interaction that is irreversible. And for this, the observer does not have to be intelligent at all. That is to say, the moon really does exist even when no one is looking at it, because the moon is a huge macro system in which irreversible interactions occur continuously. When measuring a quantum system in the state of superposition, the observer becomes entangled with it and splits into all possible versions of himself. As a result, for any other outside observer, he himself appears to be in a state of superposition. Then the second observer observing the first also becomes entangled with him and splits into all possible versions of himself. This process continues until the entire universe is involved. I repeat, this entanglement is called decoherence. What we perceive as the collapse of the wave function is nothing more than our fundamental inability to untangle the object and the environment with which it is entangled. Any solid body consists of a collection of atoms, which in turn consist of electrically charged particles. However, due to classical chaos, no collection of charged particles could remain stable under classical laws of motion. Positively and negatively charged particles would simply break away from their places and collide with each other. Only powerful quantum interference between the different trajectories of charged particles in parallel universes prevent such catastrophes and make the existence of solid matter possible. But again, if we can already make even molecules interfere, why can't we do the same with the moon? Because of the complexity. A few molecules are nothing compared to a huge cosmic body.
And to maintain superposition, the quantum system must be completely isolated from the outside world. You can't even imagine the isolation required to put the moon in a state of superposition. All the photons that could be reflected from its surface would have to be removed, because if even one photon did so, it would be an irreversible interaction and the superposition would disappear. Similarly, we would have to cool our satellite to absolute 0 Kelvin, because at any temperature above 0, the moon would emit photons into the environment. The absorption of these photons by anything would be an irreversible active interaction. But even if all of the above conditions were met, it would still not work, because just one atom flying past the moon and changing its trajectory under the influence of its gravitational field would produce an irreversible measurement. The problem of isolating a quantum system from the outside world is the main problem in building quantum computers. Although the vast majority of experts still agree that the creation of full-fledged quantum computers is only a matter of time. Quantum computers will solve problems in matters of minutes or even seconds that would take conventional computers hundreds of billions of years to complete. How is this possible with parallel universes? While a conventional computer performs operations sequentially, a quantum computer performs all tasks in parallel using the phenomenon of superposition. For example, using a quantum algorithm called Shor's algorithm to factor a number of 250 digits, the number of interfering universes would be around 10 to the power 500. That's a mind-bogglingly huge number. David Deutsch suggests trying to explain the principle of Shor's algorithm without invoking parallel universes. I mean, not predictions of what the results of Shor's algorithm will be, since it is sufficient to solve a few consistent equations for that. I am asking you to explain how Shor's algorithm factors the number, using approximately 10 to the power of 500 times more computing resources that can be seen with the naked eye. Where is this number factored? There are only about 10 to the 80th power atoms in the entire visible universe. This number is negligible compared to 10 to the 500 power. Thus, if the visible universe represented the entirety of physical reality, then physical reality would not even remotely contain sufficient resources to factor such a large number. Quantum computers already exist today, but their computing power leaves much to be desired. To make them more productive, it is necessary to increase their complexity, and the more complex they are, the more acute the problem of isolation becomes, since the speed at which a quantum system becomes entangled with the surrounding world is the higher the more complex it is. That is why neither the moon, nor Schrodinger's cat, nor even a speck of dust suspended in the air can be in a state of superposition for any measurable period of time. Do you even know what time is? We all think we know, but only until we're asked to explain it. Quantum theory, and in particular its multiverse interpretation, offers among other things a completely new concept of time, because the idea of time we have now, according to Deutsch, is contradictory, internally inconsistent nonsense. For millennia, we have thought of time as a flowing river. The present moment, which we call now, is not stationary but is constantly moving towards the future, or that moments from the future rush past the present to become moments of the past. If you sit down and calmly think about these statements, it may seem that there is something deeply paradoxical about them. Like this: we have a certain true, unique now, and everything else is either a future that has not yet come, or a past that has already happened. And only we, humans, who are attentive to the surrounding reality, are fellow travelers of this true now. Of course, from the point of view of a particular observer, a particular moment does stand out, and only this particular moment can be called now by the observer, just as the specific position of the observer in space stands out as here. However, despite the fact that space is three-dimensional and time is one-dimensional, objectively, no moment has greater privilege to be called now than all the others, just as no place in the universe has greater privilege to be called here than all the others. Deutsch writes, "People understand that here exists only subjectively, but they do not realize that now is also a subjective category. There is no objective now in nature, just as there is no objective here. Do you understand? There is no present. It's an illusion. Space-time is sometimes called the block universe because in it, all physical reality, past, present, future, is represented once and for all frozen in one four-dimensional block. Nothing moves in relation to space-time. What we call moments are certain layers, or as Deutsch says, snapshots of space-time. And when the content of these layers differs from each other, we call it change or movement. In accepting this model, we notice that our consciousness exists in all moments when we are awake. Are the various snapshots of the observer in some mysterious present? In turn, they also do not become aware of their present in turn. Each snapshot of the observer perceives its moment as now. They are all conscious, and subjectively they are all in the present. Objectively, however, the present does not exist. According to this concept, we do not feel that time is flowing or passing. Thanks to entropy, we feel the difference between our present sensations and our present memories of past sensations.
This concept could be classified as common kitchen wisdom if it weren't for the experiment proposed by John Wheeler. Initially, it existed only as a theoretical model, but in 1999, researchers carried it out physically. The essence of the experiment is as follows. We take a typical setup for emitting single photons, but behind the barrier we mount a BBO, barium borate crystal, which converts one photon into two entangled photons of lower frequency. And since these photons are in a state of quantum entanglement, measurements on one of them allow conclusions to be drawn about the other without direct interaction. A lens is placed slightly to the side, configured so that it always combines photons coming from the upper and lower slits and detector number 1. In this way, the lens destroys the data about which slit the particle passed through. Next, we perform a series of measurements with another pair of entangled photons emerging from both slits, each of which is directed to its own beam splitter, configured so that the photon has a 50% chance of being reflected downward and the same chance of passing forward. The reflected photons combine, making it impossible to determine their original slit. In other words, if detector number 4 is triggered, we have no idea about the photon's trajectory through the slits, which is called quantum erasure. Note, detector number 2 is capable of registering photons exclusively from the upper slit, and detector number 3 only from the lower one, and although this may seem confusing, the results are striking. Because when detector 2 registers a photon, its entangled partner, registered by detector 1, demonstrates the wave nature of the particle, as we observe two bands, an interference pattern. A similar pattern occurs when detector 3 is triggered. So far, nothing surprising. Detectors 2 and 3 provide information about a specific slit. But when detector 4 detects a photon, the interference pattern forms simultaneously on it and on detector 1. Although we know which slit the photon passed through since detector 4 was triggered, the interference persists. Perhaps you don't see anything extraordinary yet, but there is one aspect that is truly astonishing. The path to detector 1 is significantly shorter than the paths to detectors 2, 3, and 4. Therefore, the photon is always registered by detector 1 much earlier than its entangled twin is detected by the other detectors. The most striking thing is that the interference or two-laned pattern on detector 1 appears before the entangled photons reach the beam splitters. In other words, the detector seems to predict whether its partner will reflect off the beam splitter or pass through it. This phenomenon has been reproduced many times in subsequent experiments. It seems that the future measurement of a photon influences its past state, which is a direct violation of cause and effect. I find it tiresome that in modern physics, causality is hypothetically violated everywhere. Binary black holes, wormholes, the initial stages of the Big Bang. When we see a paradox, we fall into despair, trying to resolve it with the help of complex principles of self-consistency. But first, is the existence of causality indisputable? And second, the multiverse interpretation elegantly resolves these issues. In a static block universe, nothing changes, and one region of space-time cannot influence another more than one part of an unchanging three-dimensional object influences another part of it. For our perception, they exist not in some external space, but on our timeline. However, in essence, our timeline, every moment of time, is a different universe, and from David Deutsch's point of view, this is precisely how time works. If this is true, then it is not surprising why time is so illusory and transcendent. Who knows how many universes you have changed since you started watching this video? Therefore, if we ever travel back in time, it will create no contradictions. Killing your own grandfather will not create paradoxes, since traveling back in time will turn out to be a transition to completely different universes, in particular, those where a person with your genetic code was never born.
In the delayed choice experiment, the future does not affect the past. Photons demonstrate interference or double-slit pattern simply because all possible futures already exist, as do all possible pasts. All information from the beginning to the end of time simply exists in the multiverse, and in this context, the multiverse interpretation is absolutely deterministic. The end of the universe has already happened, all possible has already happened, all scenarios have been written and exist on different probability branches, or, if you will, intersections of the multiverse. And if in addition to other versions of me in other universes, there are numerous absolutely identical copies, then the question of which one is me only acquires physical meaning if we assume the existence of some reference system outside the multiverse with which to answer I am the third from the left. But what can be left, and what does 3 mean? Such terminology only makes sense if we imagine that images of me are arranged in different positions in outer space, but there is no outer space in the multiverse, just like there is no outer time. All existing space and time is contained within it. The multiverse simply exists and physically represents everything that is. So if you've ever wondered what came before the Big Bang, or what will happen after the Big Crunch, if it happens, you can now lose interest. The multiverse does not begin or end. These terms imply a flow of time that does not exist. Only the idea of the passage of time makes us ask about the before and after of all reality. We exist in a multitude of variants across universes called moments, each variant unaware of the others directly, but possessing evidence of their existence, for the laws of physics connect the contents of different universes. No illustration, even approximately, can convey the appearance of the multiverse. Any visualization is only a truncated likeness, but sometimes it seems to me that for a split second I am almost able to imagine it, although you may shake yourself considering all of the above to be nonsense.
True, the multiverse interpretation requires that an infinite number of new universes arise at every moment just to explain the notorious interference pattern in the slit experiment. I repeat, universes do not arise, they already exist, and paradoxically, the many worlds interpretation does not multiply entities. It requires nothing beyond mathematical apparatus. Many consider it not even an interpretation, but a direct reading of the equations of quantum theory. By trying to explain quantum mechanics differently, we only exacerbate the confusion. Therefore, in Davidovic's interpretation, the many worlds interpretation is currently the best explanation of the structure of reality. As we can see, it answers many questions, including philosophical ones. It explains why what we call free will is possible, and why this freedom has nothing to do with chance, and there are no contradictions here. The multiverse interpretation even closes the explanatory gap in Darwin's theory of evolution, responding to claims about how such complex adaptations could have developed in a short period of time. In a historic correspondence, the eminent physicist Bryce David raised a number of technical objections to Everett's multiverse theory, each of which he claimed refuted it. Devitt concluded his argument with an informal note, pointing out that he simply could not feel himself splitting into multiple copies with every decision. Everett's response echoed Galileo's argument with the Inquisition. Do you feel the earth moving? David conceded defeat. And yet that defeat is exactly what makes this story so powerful. In science, conceding doesn't mean losing. It means the boundaries of understanding have just been pushed further out. Everett's idea, once dismissed, now stands as one of the most daring answers to the question of what reality truly is. If even the greatest minds admit they cannot feel the universe splitting, perhaps that only shows how strange and vast it really is. And maybe that's the point. Reality is not here to fit our feelings, it is here to be discovered. If this journey left you with more questions than answers, good. That's what science is supposed to do. So let me ask you, do you think the multiverse is real? Drop your thoughts in the comments, and don't forget to like and subscribe, because in the next video, we'll dive even deeper into the mysteries that shape our universe.